Hello everyone. Today we are going to present our rear wing design for Formula One car. I'm going to start with a little introduction of the aerodynamics of the Formula One car. Aerodynamics is defined as the movement of air around objects. In this case, the object is a Formula One car. Aerodynamics has been an important element in the design and performance of F1 cars and racing cars in general. Aerodynamics in F1 cars is similar to that of the aerodynamics in vehicles on the road, which is to minimize drag and to improve stability. The FIA prohibits underbody aerodynamics, so the modifications that can be made to maximize the aerodynamic efficiency of the F1 car are by changing the front and rear wing cross sections. The F1's overall performance is dependent on the front and rear wings, but we are only focusing on the rear wing for this design. The rear wing of a F1 car is designed to improve driving performance and cornering stability. The rear wing must generate a significant amount of downforce while driving at low speeds such as cornering. Next, we will look into the downforce generated by the rear wing. So downforce is defined as the downward force acting on a car due to its aerodynamic properties. To improve the driving stability, the angle of attack can be increased and a substantial amount of downforce is generated. The downforce would drive the tires further into the road, giving the tires more traction. More grip leads to faster cornering speeds, more challenging acceleration and bar braking, and a faster lap time. With a greater angle of attack, the effectiveness of high-speed cornering will maximize lap time. However, due to high drag values, fuel consumption also rises. To compensate for this downside, when driving at high speeds on a straight track, the angle of attack can be reduced, minimizing downforce and drag. As a result, fuel consumption will be reduced. Next, we will look into some of the research that has been done by some researchers. According to Katz, the downforce improves traction, but not as significant as braking and cornering. When making a turn, braking reduces the cornering force, resulting in an unprecedented slip. As a result, downforce levels must be raised enough to deter the slip from happening while making a turn. However, the consequence for unnecessary downforce is an increased drag. Therefore, the challenge is to maximize the combination between the downforce and drag forces produced to attain the fastest possible time around a racetrack. So this figure illustrates the findings by Towett regarding the contribution of various components of a 2009 F1 car to the overall downforce and drag. Based on these findings, a crucial conclusion can be drawn. All parts of the car communicate with one another and function as a whole. For example, if a part is damaged during a collision such as the front wing, the loss of downforce would be greater than 30%. The front wing is intended to divert the flow away from the tires and provide a channelized flow to pass under the surface. These components' drag and downforce values will change as a result. Hillhurst and Huminick made related findings to Towett. So the figure shows that the main downforce generating components are the car wings and the floor diffuser combination. Since F1 rules only allow for the use of a flat bottom, no floor design variants can be studied. The rear wing is a vital feature of an F1 car, even though it has high drag. According to Towett, The loss of the rear wing during a collision will result in a loss of up to 40% of the overall downforce and makes the car undrivable. The loss of the front wing, however, can be repaired by replacing the nose part, which takes less than 10 seconds to replace. The flap of the rear wing is allowed to be lifted or opened by the FIA by a certain amount to minimize the drag and the downforce. This is only permitted to operate on some sections of the racetrack, usually straights, that require less downforce, and if the car is behind another car separated by less than a second. Towed also stated that when the flap is lifted, the drag and downforce levels decrease by 20 to 25%, allowing the car to drive faster for more overtaking opportunities. That's all from me.
Hello, I'm Kisheng. Now I will talk about our design selection and design concept. As you can see that there are three types of spoiler that are here, which are pedestal spoiler, lip spoiler, and lighter spoiler. And the first one is pedestal spoiler. This happens to be one of the most common type of spoilers to be seen on vehicle. And the spoiler can be simply attached onto the rear of the vehicle using bolts and nuts to hold the spoiler in place. The main purpose of this type of spoiler is to allow the wings of the spoiler to be able to generate downforce by allowing it unrestricted access to undistributed air. Besides that, this type of spoiler can be custom-made to any shape to accommodate the different type of car aerodynamic. As the spoiler is fixed on steel which hold the spoiler in a determined position, the height and angle of attack of the spoiler is usually fixed, and any changes made to it would usually require tools which a normal driver would not carry around in the vehicles. And the next is lip spoiler. Okay, lip spoiler is a type of spoiler that is usually mounted directly to the boot cover. The installation of the spoiler is also less obvious when compared to the pedestal spoiler, and the majority of this type of spoiler do not require much modification to the vehicles, as is usually applied to the car by adhesive strip on the inside of the bumper to stick to the car. Lip spoiler usually serve aesthetic purpose, as the angle of the spoiler does not have a big changes on the aerodynamic of the vehicles. And the third one is lighter spoiler. This is a totally different type of spoiler that has a source light emitting from the spoiler, usually in form of third brake light or as turn signal installed at either end. This type of spoiler is usually made with the same material as the bumper to provide the rigidity needed to support the extra weight of the light and control in the spoiler. For example, fiberglass, which is mounted to form the shape desired during manufacturing, and ABS plastic, which is more resilient to heat and ultraviolet light exposure. Fiberglass is chosen for its malleability, which is formed into multiple shapes and sizes. ABS is usually chosen for its characteristic of ultraviolet light resistance, allowing the wing to have relatively low maintenance.
Okay, thank you, Ki-Heng. So my name is Andrew and I'll be presenting on the design concept for my part of this presentation. So the design that we have chosen to go with is the F1 spoiler that is based off the pedestal rear wing design. So this design will allow the driver to change the angle of attack, which reduces the drag force acting on the rear wing, which we can see later when I'll show you the angle of attack. So this allows the driver to have higher top speed at straights and allows the driver to also make turns at higher speed. This in return will also have a maximized downforce, which also improves the grip. Next, I will be talking about the pedestal rail wing. We have chosen this design because it allows for maximum downforce generated and also an improved reduction of drag. So on the right hand side we can see the picture of the design. So we have done the majority of the design using AutoCAD, which is more simple and easier to use when compared to SolidWorks simulation. So from the isometric drawing we can see that the width of the wing is 750 mm and then that the height of the wing is 645 mm. So next we will alter the angle of attack from 5 degrees to 10 degrees to 15 degrees and finally to 20 degrees. This will be done when using simulation, when we are doing the simulation. So by changing the angle of attack, we can see from the pictures above from 0 degree to 10 to 5 and then to 15. So the design that we have chosen has a fixed upper rear wing, which is the top part of the wing, and then a manipulatable bottom rear wing. This allows the driver to change the angle of attack, and depending on which part of the course he is at, to change the drag generated and also the downforce that is generated from wind passing through the rear wing. So next I will talk about the simulation of the rear wing. So by using SimScale in SolidWorks 2019 version, so we have set the parameters as such. The enclosure of the simulation on the x-axis is from 2.7 meters to 8 meters. At the y-axis is from 0 meters to negative 2.7 meters, and on the z-axis is from negative 0.1 meter up to 2 meters. Then next we have also chosen an incompressible fluid flow. This is due to ensure that our data is correct and no errors are generated from disruption in air. So the fluid that we have chosen to use is air and has a kinematic viscosity of 1.592 times 10 to the power of negative 5 meters square per second. Then air has a density of 1.196 kg per meter cube. So next, this is the simulation boundary that we have set, which can be seen on the picture on the right hand side. So the velocity of the inlet is ranging from 90 meters per second up to 360 meters per second, with intervals of 180 meters per second and 270 meters per second. The minimum pressure of the outlet is 0 kilopascals. So next, the simulation conditions that we have set for this simulation are the runtime of 1000 seconds and a data write interval timing of 1000. So for every 1 second that the simulation is running, one set of data will be generated. Then next the maximum runtime is 100,000 seconds. So next is the mesh condition of the simulation. On the x-axis is from 3.2 meters up to 6.4 meters. And on the y-axis is from negative 2.7 meters up to 0 meters. And on the z-axis is from 0.4 meters.
Okay, hi, I'm Tai Manwei. I'll be continuing by doing calculations, discussion, and also conclusions. So we'll be calculating the spoilers area. For the lower rear spoiler cord, we'll be taking the values of 560 degree over 360 degree. We'll multiply by 2 pi and then we'll multiply by 310. We'll be getting 270.33 mm. And as for the area of the lower spoiler, we'll be getting 0.2029 meters. As for the upper rear spoiler cord, we'll be taking 32.82 degree over 360 degree multiplied by 2 pi multiplied by 275, and then we'll get 157.52 mm. And the area of it will be getting 0.1181 meters. And the total area of the rear wing will be 0.3209 meters. This is the table when we find the difference of changes in data when we're manipulating the angle of attack. So for the drag force, The formula is Fd equals to 1 over 2 times Cd times density times velocity times area. From this, we'll get the value of all of this according to each angles. And then for the percentage changes, we'll use the last calculated value minus the current value divided by last calculated value, and then we'll multiply by 100 in order to find the change. So onwards, this is the graph that we have gotten after we do the calculations for it. This is the graph for lift force against angle of attack. As for this graph, it's a graph of percentage change in lift force against the angle of attack as it changes every time. This is the graph for drag force against the angle each time it changes. And finally, this graph is the percentage change in drag force against angle of attack. To sum up everything that has been stated so far, we're able to understand that the Formula 1 rear wing is a tool or attachment that allows for increase in the generated downforce generated as wind flows through it. So the rear wing is able to reduce the drag force as it improves aerodynamic of the car, where the wind passing through the rear wing can be viewed to split into two parts flowing through the upper part as well as the lower part. This separation is what causes the rear wing to push down on the vehicle, generating downforce. So by changing the angle of attack of the rear wing, we're able to achieve different amounts of downforce and lift force generated by the wing. So for example, we'll be changing the angle of attack from 0 degree to 20 degrees. And we're able to see that the flow of wind changes from being a limited flow to the turbulent flow as the angle of attack gets more and more aggressive. This can be observed when the angle of attack changes from 10 degree to 15 degree from the table earlier, that the air that flows through the rear wing creates a vacuum area behind the rear wing, which in return causes the air to experience turbulent separation, which negatively impacts the function of the rear wing. So other than that, from the simulation, we are able to set parameters such as having a fixed upper wing that does not change no matter what the conditions. By doing this, the results obtained by altering the lower wing is easier to oscillate without any extra factors that will change the data obtained. So the speed of the wind passing through the rear wing is also limited as at certain points to make sure that the data obtained when running the simulation is accurate and not dependent on random errors. So for example, we will use different speeds from 90 meters per second, 180 meters per second, 270 meters per second, and 360 meters per second. So by factoring all these parameters, we are able to show that by increasing the angle of attack from 0 degree to the next one of 10 degree, results shows that a slight increase in the downforce, and by increasing the angle of attack from 10 degree to 15 degree, we are also able to see the measurable difference in the downforce and drag experienced by the rear wing. So after conducting the simulation, we're able to conclude that the maximum lift force that can be generated by the rear wing is 10 degree. So of course, for the precaution, we always need to run the simulation at least 2 times so that the result of the average data will be gotten. This is to ensure that the data obtained by the simulation can be as accurate as possible, so to reduce the random error occur when running the simulations. Other factors that might affect the result might be that the rear wing is only a computer render and that an actual design could not be tested in Malaysia currently, so due to COVID-19 virus. If we are able to make the physical model of the rear wing design, we'll be able to get more accurate and closer real life data compared to the simulated ones, as it does not have any other errors. In conclusion, after running all simulations and performing the required calculations, Our group was able to obtain a respectable set of results. The design of the rear wing that we have done, it passes the rules and regulation for Formula One racing. So this design of our rear wing will be able to apply on the rear one. And after doing all this, we have a deeper understanding on what makes the Formula One car and more understanding on the downforce and the lift force concept for everyone, as we have to run through all the calculations and also the simulations. Thank you very much, and that is all from me.